Welcome. This video is going to take a closer look at equilibrium and kinetics in the industrial setting. Remember, industry is about producing lots of product quickly. So lots of product is your yield or equilibrium, and then versus the rate or kinetics. And IB likes to look at 3 case studies in industry because they produce important compounds for different reasons. The Haber process produces ammonia to help grow the world's food supply. Methanol is the most important or most common chemical feedstock, and the contact process produces sulfuric acid, which is the most widely produced chemical in the world and is used in a lot of industrial processes. In fact, I've got it showing down here a summary. Agricultural, for both phosphate and ammonium sulfate fertilizers, soaps, detergents, plastics, dyes, pigments, and paints, and then car batteries, electroplating, pulp, and paper. So that's a wide variety of industries that rely on sulfuric acid. So in the early 1900s, world hunger was a growing and serious concern because ammonia and nitrogen is needed for plant growth, and Mother Nature cannot keep up with the demand. And what I mean by that is that soil was becoming depleted because crops were being planted and not rotated to put back in the nutrients they needed to. And at that time, we didn't have fertilizers like we currently use. So Fritz Haber came up with a way to synthesize ammonia in the lab, which is credited with feeding a third of our population, which is 2 billion people per year right now. And it's said to generate half the protein within human beings. So people certainly wouldn't be as healthy as they are, and we certainly wouldn't eat as well or as much without the Haber process. And it's a big deal because 80% of the air is nitrogen, but nitrogen is mostly unavailable to plants because nitrogen is so unreactive with its triple bond and its high electronegativity. But it has negative impacts because ammonia is also used in explosive because that nitrogen bond isn't stable when we take it out of N2, when we make it into other things. So Haber, in effect, helped Germany sustain and win World War I. And in fact, the process has been responsible for killing many people in many wars. Plus, there's pollution concerns with its productions, and it's dangerous to produce. Remember, it's an explosive, and in fact, Le Chatelier was actually working on this same process when he had a huge explosion in his lab, and he abandoned trying to develop this process and just said it wasn't worth it. In fact, it was one of his greatest regrets because he figured it cost him the Nobel Prize, which Haber ended up winning. So whether you think it's good or bad, the bottom line is it's a process that's been developed. And so what IB expects you to know is that given this reaction, N2 plus 3H2 yields 2NH3, you should be able to look at this reaction, not memorize it, but look at it, and you should notice that all 3 components are gases. The total number of molecules is reduced from 4 on the reactant side to 2 on the product side. It's an exothermic reaction in the forward direction, and you'd be given delta H for this so that you know it's exothermic. And so what they would expect you to do is to be able to come up with some ways to maximize the rate and the yield. So one way to maximize the rate and the yield is to supply the nitrogen and hydrogen in a 1-to-3 ratio. Okay, so it's the optimum ratio. And then remove NH3 as it's produced. So keep a constant supply in that 1-to-3 ratio, but remove product. So that's going to help drive your equilibrium to the right. Since the moles of gas decreases with product, high pressure would increase your equilibrium. So usually this experiment's run around 200 atmospheres, which that's a lot of pressure. It's 200 times more than what our atmospheric pressure typically is. That's expensive and it's dangerous, but that's kind of the norm that's used. The high temperature would increase the rate, but it would cost more and it would decrease the yield. So instead they usually use what's called a moderate temperature of just 450 degrees Celsius. And they use a catalyst to speed up the rate to offset that loss of rate with the somewhat high temperature for the rate. And the catalyst is usually this iron powder. What's interesting is even after maximizing all these things, the yield is still only 10 to 20% NH3 being produced. But it's pretty easy to recycle the unreacted N2 and H2. Just keep cycling it back through the same system, and eventually they do get a 95% yield from this reaction. The contact process is used to make sulfuric acid, and on the earlier slide I showed you all the uses of sulfuric acid. So it's the most commonly produced and consumed chemical in the world in industry. And it's called the contact process because the O2 and SO2 to start this whole reaction react in contact with the catalyst, which happens to be vanadium oxide. So it's really a series of three reactions. You combust or burn sulfur, so S plus O2 gives you the SO2. And then the second step, which is oxidizing the sulfur dioxide or combining SO2 with O2 to give you SO3. And finally, the third step, SO3 with water then synthesizes to give you the H2SO4, which we wanted. That second step, though, is the important one because the overall rate depends on step 2 because it's the slowest step. So whatever your weakest link or slowest step is, that's what's going to hold up the whole process. So that's why there's a catalyst used in step 2, and hence the name contact process, because the SO2 and O2 have to be in contact with that catalyst. So what IB will expect you to know is if they give you just the second reaction, that's the one to focus on, the 2SO2 plus O2 gives you SO3, they would expect you to be able to look at this and figure out ways to optimize it. Well, again, it's an exothermic reaction. You go from 3 moles of gas to just 1 mole of gas. So pressure will favor your forward reaction. You'll want to use a moderate temperature again so that you don't give up the entire rate for yield and you don't give up the entire yield for rate, so you kind of meet in the middle on that. And then you use a catalyst to offset that slower rate from using a lower than desired temperature. And then the third process is the production of methanol. Methanol is an alcohol. It's another important chemical for industry because it's used as what's called a chemical feedstock, which means we use it to make other chemicals, especially methanol. And methanol is then used to make plastic, paint, explosives, and plywood. So methanol or methanol are both commonly used. Methanol is used as a solvent, it's used as an antifreeze, and it's helped to produce biofuel. And they're also looking at ways to use methanol to replace gasoline in car engines, which in Minnesota right now we use ethanol blended gas, which is one bigger. Methanol just has 1 carbon in the alcohol. Ethanol has 2 carbons. We don't use 100% ethanol by any means. We use 10% blended gas, or E85 vehicles use a higher blend of ethanol in there. So the basic reaction for producing methanol is carbon monoxide plus hydrogen gas will yield methanol, and it's also exothermic. So to optimize this reaction, again, you're starting with 3 moles of gas and just 1, so higher pressure would increase it. And in this case, they use 5 to 10 times 10 to the 6 pascals, so that's not nearly as high as they use with the Haber process, but it's still considered high pressure. They use an even lower temperature here, 250 degrees Celsius, to help increase the rate. But it to help increase the yield, but it decreases the rate because it is exothermic. And so then they also use a catalyst on this. So what you should notice from all 3 reactions is you're using high pressure because you go from more moles to fewer moles of gas. You use kind of a moderate to low temperature so you don't completely sacrifice rate or yield, and you use a catalyst to improve the rate overall.